guys. What I'm going to do today is just kind of go through all of the things that we have learned to kind of refresh your memory, and then I'm going to leave you a practice, just cumulative practice for you guys to work on, where I'm going to have you actually showing, turn in your work as well, so I can give you some feedback. So this will be attached if you want to download it, or just kind of copy down the examples as we go. And I actually downloaded one of those calculator apps so you can kind of see how that works as well. So you can see it looks nice like a calculator and less like a phone calculator. But let's go ahead and get started. So the first section I've got is solving exponential equations, and there's two different types. One's where you can get a common base, and one's where you can't, and you're going to have to use logarithms. Okay, so if you can get a common base, we'll look at both of the bases. This is 5, this is 1 over 25. So we can rewrite those with a common base of 5. So this would be 5 to the negative 2. And then you bring down the 2x plus 4 equals 5 to the x plus 1. Okay, we'll distribute this exponent, but once they have the same base, we can kind of ignore those. So we get x plus 1 equals, multiply that out. Oh, sorry. And that gives me negative 4x minus 8. Okay, and then we just solve for x. So add 4x, that gives me 5x. Subtract 1, that gives me negative 9. And then divide by 5. So we get x equals negative 9/5. So if you have two things raised to a power, see if you can get a common base first, and then rewrite and solve. Okay, so on the second example, really there's only one base here anyway, so it's hard to get a common base, but we need to solve for that first. So add 3 to move that over. So we get 5 times 2 to the x minus 3 equals 20. And then we need to divide by 5. Don't do 5 times 2 because the 2 has an exponent, the 5 does not. So we get 2 raised to the x minus 3 equals 4. Okay, and now here we have to find a way to get this out of the exponent. And actually you could use common base here. I didn't mean for that to happen, but I'll show you how to do it without a common base as well. So we need to use log base 2, okay, if we want to cancel out that 2. So on the right side, well, we should know what that is, but on here, just so I can show you that log A button, we can do log base 2 of 4. Okay, and that gives you 2 because 2 squared gives you 4. And then we're left with x minus 3 on the left, and then solve for x. So add 3 and we get x equals 5. Okay, so those are our two types of exponential equations. So you can look through those and see when you need to use a log or when you can get a common base. Okay, the middle part, we're looking at log equations. So we kind of have two different sections here. One where we end up with a log equal to a log, and then one where we end up with a log equal to a number. First thing you always want to do is try to condense where you can. Okay, so remember addition, you can condense by multiplying the arguments. So we do log base 2, and then multiply those together. That gives me x squared minus 5x. And then on the right side, we have log base 2 of 6. And if we have a log equal to a log, then we can kind of drop those and set their arguments equal. So x squared minus 5x equals 6. And then we need to get this equal to 0 so we can factor and solve. Sorry, this is blurry. Subtract 6. So x squared minus 5x minus 6 equals 0. Then factor by multiplying to negative 6 and adding to negative 5. So that gives me x minus 6 and x plus 1. So our two solutions would be 6 and negative 1. Okay, and with these, your extraneous solutions can occur if when you plug that back in, it would give you a negative argument. So if I plug in 6, 6 minus 5 is positive 1, 6 is positive 6, so that is positive. But if I plug in negative 1 minus 5 gives me negative 6, and I'm not allowed to have a negative or a 0 there. So we would have to throw out the negative 1 and x equals 6 would be our only answer there. Okay, so second one, same thing, we want to condense where we can. Now this one is subtraction, so we need to divide our arguments. So this would be x minus 2 divided by 4 equals 2. Okay, and now here we can't just drop the log, we've got to get rid of the log. So this is where we exponentiated, and we would use the same base as we had here. So we want to use a base of 3, and these are going to become our exponents. So it's going to cancel this out. So we end up with x minus 2 divided by 4 equals 3 squared, which is 9. And now we can solve for x. So times 4, so we get x minus 2 equals 36. And then add 2, so we get x equals 38. Okay, and if we go to plug that back in, 38 minus 2 will be a positive value, so that one is a good solution. It's not extraneous. Okay, so these were all the equations we were working on before our hiatus here. Okay, and then these two are the two interest formulas that you guys kind of learned this week. So I'll go through those, and also somewhere you're having to solve for an initial value or an exponent, because I think that's where pretty much the only issues were. So we have two things, compounding n times per year. So this is where we use p times 1 plus r over n raised to the nt, and then compounding continuously. Sometimes you'll hear that called the PERT formula, PE raised to the RT. Okay, so number 6, suppose John invested $2,000 at 3% interest rate, compounded semi-annually. How much money would he have after 5 years? So his investment is his P, so that's 2,000. Then it's 1 plus R, so 3% is a decimal, will be 0.03. N is the number of times it's compounded. So semi-annually means 2 times per year. So I'm dividing that interest rate into 2 times. And then N times T, so twice per year for 5 years. So 2 times 5 or 10. Okay, so we'll do 2,000. 1 plus 0.03 divided by 2. And then we are raising this to the 10th power. Oops. And then that gives you a big long fraction. We can change that to a decimal. So 2,321.08. Okay, so that's how much money he would make. And I would be careful using these types of calculators. I would try to go ahead and multiply those because sometimes it may mess up your order of operations. All right, now letter B, we're going to do some solving. It says, how long would it take him to have $3,000? So we're actually going to look for our time here. So we're going to use our same equation, 2,000, 1 plus 0.03 divided by 2. And now it's going to be 2 times t. We want to know when is this going to equal 3,000. Okay, so now we're kind of solving an exponential equation like we did on number 2. So we need to get this base by itself. So divide by 2,000. Okay, so 1 plus 0.03 divided by 2 raised to the 2t. And then 3,000 divided by 2,000, that's going to be 1.5. Okay, and now we're going to have to use a log to get rid of this base. So you can either do log base this, 1 plus 0.03 divided by 2, or you can go ahead and figure out what that is and write that as a decimal. Okay, so 1.015. So we have to do that on both sides. Okay, to cancel this out. So in our calculator, we would do log base 1.015 of 1.5. And that gives me 27.23. And then I still have 2t on the left, so I need to divide that by 2. And so that'll give us about 13.62 years. Okay, so that would be solving for our exponent there. All right, And then compounding continuously, I've got to just plug in one and then one where we're solving for the initial value. So Marie is investing $10,000 at 2.5% annual interest, compounding continuously. So that's where we use this E formula. How much money would she have after 3 years? So 10,000 E, our rate is 2.5%, so 0.025 times our time, which is 3 years. Okay, so we'll do 10,000. We found the E here, there it is. E raised to the 0.025 times 3. So 10,778.84. Hold on, buddy. Now you need to go lay down. Sorry. He's taking a nap. All right, and then letter B. If she wanted to have $15,000 in her account after 10 years, how much would she have to invest? Suppose it's still compounded continuously with a 2.5% interest rate. So now we are solving for our initial value, our interest rate, okay, still the same. We're going 10 years, and we want to end up with $15,000. Okay, so we have to solve for P. So we need to get rid of this, which is being multiplied. So we're going to have to divide by that value. So you can either divide by that, E raised to the 0.025 times 10, or you can go ahead and get that as a decimal. Some people like doing that. Okay, which is about 1.2840. And we're taking 15,000 and dividing 15,000 by that number. So 1.284025. So try to just put as close as you can. So that gives me our P value, which was 11,000. Ooh, I did something wrong here. Oh, I did 150,000. 15,000 divided by 1.284. So 11,682.24. Okay, and that will solve for your initial. So if you need your initial, figure out what the other value is, and then you're dividing by that, either exactly how it is or go ahead and put it as a decimal and divide there. Okay, just try to keep some decimal places so you're as accurate as you can be. All right, and then lastly, we're going to talk about graphing the log functions. Now, if you need to graph, you can always use Desmos online or the app on your phone, or if you have a graphing calculator, obviously you can use that. But I'm not going to make you graph it on here, just mostly finding the transformations and getting the characteristics. So remember, log functions have vertical asymptotes, and they're either going to look like this, okay, if your base is less than 1, okay, or like this, if your base is greater than 1. So your transformations, mostly we're just going to do H and K. So we've got log base 4 of x plus 2 minus 3. So this is going to shift left 2 and down 3. Okay, so remember the H value is telling you where the asymptote is. So it's shifting left 2, and then it's kind of going up from there. So our domain starts at -2 and then goes to infinity. So it's going to be whatever makes the 0, that's going to be your starting point, or wherever you shift, you start at 0 and shift left 2, that puts you at -2. You need to use a parenthesis because you can't make it equal exactly 0, it's got to be greater than 0. Our range for these are always going to be all real numbers because they'll go up and down forever. And then your asymptote comes from your H, and it's x equals. So this would be x equals -2 for our asymptote. Okay, and then the last thing we did was inverse. So what we have to do first is switch our x and y. So we're going to do x equals log base 4 of y plus 2 minus 3. Just using that same function, switching your x and y, and then we solve for y. So add 3 on both sides. So we get x plus 3 equals log base 4 of y plus 2. Okay, and now we're going to have to get rid of this log. So use a base of 4 and do the exponentiating to cancel that out. So 4 raised to the x plus 3 equals y plus 2. And then last step, to get y by itself, subtract 2. So we get 4 raised to the x plus 3 minus 2 equals y, and that would be our inverse function. Okay, and you could always take these and graph them on Desmos and make sure they're symmetric over that line y equals x. But this is kind of a quick recap of all of that. We're going to use a new program to try to turn in our work, and we'll see how it goes, but I'll post the directions on that in the work time section. Thank you.